Okay, so the spectroscopic technique that I'm going to be talking about is UV-Vis spectroscopy. Here are the table of contents, and let's go through them one by one. So starting with introduction to UV-Vis spectroscopy. So UV-Vis spectroscopy is generally a term that's used for ultraviolet visible spectroscopy. It is a type of electronic spectroscopy that measures the absorbance of light in the range from UV to visible, that is from around 200 nanometers to 800 nanometers. However, there are spectrometers which can measure up to near infrared region as well. So the basic idea behind UV-Vis is that the light that's incident on the molecule results in the absorption of the energy by the electrons in the ground state that absorb this energy and get excited to the excited state. This excitation results in the absorption, which is what we see in the absorption spectrum. And this electronic transition can be described when we use Bohr's energy relation, which is the delta E, that is change in the difference in the energy states, that is initial minus final energy states, equals to h mu, where mu is the frequency of the light, or equals to hc by lambda, where lambda is the wavelength of the light, h is the Planck's constant, and c is the speed of light. UV spectroscopy is generally a non-destructive technique. It's rapid and it's cost-effective, which is why it's mainly used in a lot of qualitative and quantitative analysis. The basic theory behind UV absorption, so like I talked about absorbance, Beer-Lambert law relates this absorbance using molar absorptivity, path length, and concentration of the sample. Although the only limitation to Beer-Lambert law is that it's applicable only as long as the solutions are dilute as well as homogeneous. So a typical UV spectrometer consists of a polychromatic light source. You have a monochromator, which has some kind of dispersion grating, and you have a detector, which is usually a photodiode array. The samples are usually placed in quartz or fused silica cuvettes because you want them to be UV transparent. Electronic transitions, when happen within the molecules, do have to follow certain selection rules. Some of the major ones are Laporte rules, spin multiplicity, and orbital coupling. I have divided it in 3 different categories to understand the different electronic transitions seen in different molecules. When we talk about organic molecules, we usually talk about transitions that happen between molecular orbitals, that is sigma and pi. And this is explained very well using molecular orbital theory. When we talk about inorganic compounds, we usually talk about transitional metal complexes, and they show transitions in the visible range as well because we have strong charge transfer transitions. In semiconductors, UV spectroscopy can be used to estimate the optical band gap, as it can look at the transitions that happen between the valence band and conduction band, although certain defect states may affect the results. On the left here, we see an image where we see that the direct electronic transition from E0 to EX results in a sharp peak. However, in usual UV spectrum, we know that we get a broader peak, and that's because the electronic transition is not just the only transition that happens, but the broad peak encompasses all the other vibrational and rotational transitions that may happen within the electronic regions. So keeping that in mind, let's look at the recent examples. So the very first paper that we are going to probe into is predicting the size of silver nanoparticles from their optical properties. This paper was published in 2020 in the journal Plasmonics by Amir Jani et al. What they tried to do here is that they try to use UV spectroscopy as an experimental technique and me theory as a computational technique, both of these two things, using them together to find out if they can find the size of the silver nanoparticle just by looking at its UV spectra and coming to an empirical equation or computing an equation to do so. For this reason, they used the LSPR positions of the silver nanoparticles, which is localized surface plasmon resonance. So what does that mean? I've given a note at the bottom. So the LSPR is nothing but it's a phenomenon that's characteristic and that arises from the collective oscillation of the conduction band electrons. And it's highly sensitive to the size of nanoparticle, the shape, as well as the surrounding dielectric environment. For this paper, they made sure that the shape of the silver nanoparticles that they synthesized were all spherical, and the dielectric environment was kept constant. So the only thing that the LSPR peak position on the UV spectrum would correlate to is with the nanoparticle size. So they synthesize silver nanoparticles of different sizes. They characterize them with UV as well as DLS to confirm for a second opinion, and they developed the equation to reliably estimate the size of nanoparticle just by looking at its UV spectrum. So when they did the silver nanoparticle nucleation and growth, while the synthesis was happening, they made sure to do real-time spectral monitoring. The initial yellow colored spectra that we see is, or the short wavelength LSPR peaks correspond to smaller silver seeds. And as we see the continuous redshift, they made sure that this was because the particle size kept increasing, because this is consistent with the known plasmonic behavior of larger nanoparticles. Like I said, it's characteristic. As the size of nanoparticle increases, the surface plasmon maxima also shifts to higher wavelengths. That was the experimental part that was concluded. Next, they used the Mie theory to understand how they can model this interaction and put them into equations. So for this, we see like a complicated bunch of equations, but we won't be going through them too much, but we would be only seeing the relevant parts of it. So the first three equations that you see are nothing but extinction, scattering, and absorption cross-sections for a spherical particle. The extinction and scattering cross-sections heavily rely on the values of AL and BL. And if you go down, we can see that the AL and BL equations have the repeating value of M. This M is nothing but the relative refractive index of a metal. So the bottleneck of using Mie theory is that it heavily relies on the refractive index data calculation used in the calculations. And before this paper was published, the one problem was that whenever they used Mie theory to correspond to the UV-Vis scene, they won't usually fit with experimental data, and that's because different refractive data index values, or even changing the value slightly, would result in large deviations in the fit. So for this paper, what they did is that they used several refractive index databases. So they started from Palick, John and Christie, and all of these values, all of these databases, and they tried to see which gave the best fit with the experimental values. And they found out that the Palick database yielded the closest match to the experimental SPR data collected, and the error margin was under 1%. They then produced a linear empirical equation, which is given here. So as you can see, you can just calculate the nanoparticle size directly from this equation as long as you have the plasmon resonance maxima value from the UV spectra. So this showed a 99% correlation with the particle sizes measured by DLS for silver nanoparticles between the size from 1 to 100 nanometers. In conclusion, the strong LSPR size correlation does show that UV-Vis can be used as an efficient alternative to more complex characterization techniques. The second example looks at operando diffuse reflectance UV-Vis spectroelectrochemistry for investigating oxygen evolution electrocatalysts. It's a mouthful, but let's go through each term individually. Operando means studying of catalysts under working conditions. Diffuse reflectance UV is a different type of UV-Vis. We generally talk about absorption or transmission UV-Vis spectroscopy, but diffuse reflectance is the third type, where the spectrometer measures the diffusely reflected light rather than the transmitted light. And the best suited samples for these are usually thin films, solid samples, and electrodes in this case. The diagram here that you see has an integrating sphere. So the incident beam is incident on the sample. It reflects photons, and the integrating sphere is usually has a reflective material all around it. It collects all these photons and is sent to the detector further. So that's diffuse reflectance. Spectroelectrochemistry is because they did UV-Vis alongside electrochemistry. So both of the data was collected simultaneously. What they tried to do is they wanted to study the structural and electronic changes that happened within the catalysts that are used for oxygen evolution reactions. They focused their attention on two main catalysts, which is zinc cobalt oxide and cobalt aluminum oxide. So they combined the UV-Vis data with cyclic voltammetry and chronoamperometry to understand different oxidation state changes and try to establish any kind of relationship between the structure and the activity of the catalysts. So here's the experimental setup that they used. So they had a spectroelectrochemical flow cell that was coupled to the UV-Vis spectrophotometer. As we can see here, they are coupled to each other. And for the measurements, this was used. The electrodes that they used was a 4 millimeter gold screen printed electrode, which acted as a working electrode on which the catalyst was going to be deposited. Platinum was the counter, and reversible hydrogen electrode was the reference electrode. The electrolyte used was 1 molar KOH. So here we see W is the waste, R is a reservoir of the fresh electrolyte, which is 1 molar KOH, P is a peristaltic pump, which supplied the electrolyte, S is our spectrophotometer, and PC is where all the data was observed and analyzed. So the spectra was recorded in real time as soon as the potential was applied. The positions of the band was either assigned manually or they used Gaussian deconvolution using origin. And they matched and identified all the electronic transitions through Tanabe-Sugano diagrams. All right. So the very first figure shows a dry sample of zinc cobalt oxide. It generally has a wurtzite type structure and it's tetrahedrally coordinated. So it has a tetrahedral symmetry in the cobalt 2 plus oxidation state. So we see this broad absorption where they identified three characteristic DD transitions that corresponded to these three transitions in the Tanabe-Sugano diagram for D7 tetrahedral configuration. Once the catalyst came in contact with 1 molar KOH, which is electrolyte, they saw that the tetrahedral cobalt 2 plus transitions completely disappeared. And we got new absorption bands at these particular transitions that corresponded to these particular transitions. But that was because the structure shifted from tetrahedral to octahedral coordination, and they assumed that it formed something like COOH twice. Also, a band additionally appeared at 396 nanometer, which they attributed to the splitting of 2H free ion term. So these are the two transitions that we see here, and this is the 2H term that they assumed might have split because of the changes in the ligand field. When the potential was started to apply from 0.9 volt, no oxidation state change occurred, but the overall absorption intensity increased. So as we can see here, the absorption is around 0.03, 0.02, but as soon as the potential is applied, the absorption intensity increased to around 0.12. The changes in the peak intensity, they assumed might have been due to zinc leaching, as a result of which there might have been structural deformation. So it went from having a perfect octahedral structure to something which is a lower symmetry state, as a result of which we know that octahedral symmetry is perfect symmetry, so DD transitions is laboratory forbidden. But when the symmetry is lower, you would have that relaxed, thereby increasing the intensity of the absorptions. As the potential was further increased from 0.9 to 1.3 volt, we see a continuous shift or redshift from around 620 to 670 nanometers. And this was because they assumed that the cobalt 2 plus is getting partially oxidized to cobalt 3 plus, leading to another structural transition from cobalt OH twice to something like COOH. And this also indicated that there is a deviation from pure octahedral symmetry to something like D3H or C4V geometries. At 1.4 volt, they saw a complete redshift to 690 nanometers, and the lower energy bands got completely diminished around here, which also kind of proved the fact that there was further oxidation to cobalt 4 plus, and a higher content of cobalt 4 plus indicates that it's getting closer to the OER. Finally, under OER conditions at higher than 1.5 volt, the absorption maximum again shifted until 720 nanometer at 1.6 volt, where the oxygen evolution started, and cobalt 3 plus oxidized further to cobalt 4 plus, but they did determine that the structure predominantly would remain COH-like. They don't know which geometry it would attain at the final voltage, but there would be a balance of cobalt 3 plus and cobalt 4 plus species. One more interesting thing they noticed was when they reduced the potential back to 1.1 volt from 1.6, the spectral intensity continuously decreased and the absorption maxima slowly shifted back to 630 to 620 nanometers, indicating that all these electronic transitions are completely reversible. And this showed that the active phase of COH that is formed is only formed during the OER step, and it returns back to its initial state when the potential is lowered back. The second catalyst of cobalt aluminum oxide, however, did not show all these exciting results. All throughout when the OER was performed, it remained in the cobalt 2 plus oxidation state in the tetrahedral coordination, and they performed XPS and XAS to confirm that as well. Even the OER onset did occur at 1.53 volts. The spectra showed only minor intensity changes and no peak shifts as we can observe here. So that was intensity changes, which was quite minor, but the peaks remained as it is, even when we increased or decreased it back to 1 volt. And this suggested that the OER activity was only surface limited and the bulk cobalt 2 plus sites remained unaffected. So in conclusion, UV-Vis could be used in accordance with other electrochemical setups to understand the structure activity relationships of different catalysts. One last example we'll be looking at it is a forensic investigation. So in this forensic investigation, a double homicide had occurred where the victims or the two bodies were wrapped in a checkered blanket, which had red, green, white colored threads, and a beige bed sprayed on top of that before they were transported in the car, trunk of a car, as we can see here, and dumped in a lake. Because the bodies were dumped in a lake, the natural fibers got exposed to water and got destroyed, but the synthetic fibers survived, which is why they became the focus of analysis. For this specific analysis, they used IR spectroscopy along with UV-Vis microspectrophotometry. So the microspectrophotometry is the analysis of small microscopic samples, which can measure light transmittance, reflectance, absorbance, and fluorescence all together. So the fibers were collected from the vehicle using tape lifting. They found beige fibers they were found widely spread in the car, but the red and green fibers were found in only specific spots that where the blanket had tears on them, which is why the fibers may have escaped. And the spectroscopic results showed that there was 50 to 70% of fibers matched those from the victim wrappings. Even though finding these fibers are pretty common, however, the combination strongly supported that there had been contact of those particular blankets and bedspreads with the suspects' vehicles and the bodies. Conclusion. So UV spectroscopy is versatile, it's non-destructive, and it can probe electronic transitions with ease. It does play a critical role in nanoscience, as we saw it in catalysis and understanding structure-active relationships. It's important. It's also applied heavily in forensic sciences and real-world applications. And this kind of sensitivity to electronic changes makes it very valuable in understanding atomic level insights, especially when we talk about energy research. It's fast, it's highly accessible, and it's cost effective. And that's why we see that it's still relevant across different applications. And ongoing advancements are trying to integrate the UV-Vis with other computational modeling and machine learning techniques to enhance its predictive capabilities. Thank you.